For this lesson on curve sketching, we hope to analyze and sketch the graph of a function. Specifically, we want what's called a complete graph. A complete graph kind of sounds like an oxymoron. How can you have a complete graph of something that's infinitely big, talking about domain and range? When we talk about a complete graph, we mean that we include all of the major details, all of the extrema, any of the asymptotes, holes, symmetry, and things of that nature. Okay, so take a look at the image here. It's so precious for being able to analyze and sketch the graph of a function. You can see this little guy, he's sketching a parabola. Meow. And there's a kind of a symmetry here. This even symmetry. So it's flipped across the y-axis, and you can see he's a big fan of Euler's number, maybe even multiplication here. Okay, all right then. So let's think about and kind of summarize all the things that you need in order to accurately draw a complete graph for your function. So the first consideration is domain and range. Domain, you've been doing since Algebra 1. What can x be? What can x not be? And usually the second question is the one that you ask yourself is, what can x not be? Range, it's not quite as obvious as all that. Usually you get that range from actually drawing the graph. Okay, some more considerations that we need to make is where the intercepts. Intercepts happen where x is equal to 0, where y is equal to 0, where are our holes in our asymptotes. Those could be vertical asymptotes or horizontal asymptotes. Holes happen where our function is undefined. That's going back to the domain. So do asymptotes, vertical asymptotes happen where our function is undefined. In behavior happens, and sometimes horizontal asymptotes happen when we consider what happens when x approaches either positive or negative infinity. And the new part of this, the calculus part of this, we take care of those, of course, with some sort of limits. Limit as x approaches a or as x approaches positive or negative infinity. We also have a period. A period happens for all of those trig functions where our function has what's called translational symmetry, where it just repeats every pi, every 2 pi, something like that. And then we have some other kinds of symmetry. We have our even symmetry and we have our odd symmetry. Talk a little bit more about those in just a second. So almost all of this stuff is pre-calculus, with the exception of the refinement of asymptotes and holes using some sort of limits. The calculus part of this, the new part, is being able to find the extrema, the concavity, and the points of inflection. And it starts with your critical numbers, where your first derivative is equal to 0 and where your second derivative is equal to 0. First derivative is equal to 0, you could possibly have some minimum or maximum points. Second derivative is equal to 0, could possibly have a point of inflection. All right, let's take a look about some symmetry, just a little bit more. Picture over here on the left-hand side, we have y-axis symmetry. Y-axis symmetry is called even symmetry. And if I were to stick a negative value in for my function, notice that I get the exact same thing I would get if I stuck in a positive value. So the algebraic test is f of negative x is equal to f of x. You just stick in a negative x, work it out, simplify it, and confirm that it's the same thing as the original function. The picture over here on the right, we've got odd symmetry. This is rotational symmetry, 180 degrees around the origin. There's an algebraic test for this one as well. If you stick in a negative x, you get the exact same thing except for the opposite if you stuck in a positive. Algebraic test is f of negative x is equal to negative f of x. All right, and then the one last piece of pre-calculus, and that's periodic functions. Periodic functions, they have a period. It's translational symmetry that repeats every period, that period most commonly, something like pi or 2 pi. And if I take a particular x value and I add my period to it, I get the same exact y value that I got before. That's called its period. It says f of x plus p is equal to f of x for all x in the domain. And that p, once again, is perhaps pi, perhaps 2 pi, depending on the trig function. Okay, so here is a kind of a recapping of all the calculus stuff about functions. F of x, f prime of x and f double prime of x. So first we have an increasing function. The function's increasing. I know the function's increasing in terms of calculus if the first derivative is positive. Likewise, we know that our function is decreasing if our first derivative is negative. That's just the test for it that we discovered in the course of these lessons. All right, and then we have critical points. Critical points happen when first derivative is either equal to 0 or undefined. What could possibly happen at those critical points? Well, we have a possible minimum point. If you have a possible minimum point here, your first derivative is equal to 0, possibly undefined, and the shape here is concave up. If it's concave up, then that means that the second derivative must be positive. What could also happen at one of these critical values is a possible maximum point. Possible maximum point, you can see here on this picture, we have a shape that is concave downward. If it's concave downward, then our second derivative is negative. Specifically, this is talking about the second derivative test. We also have a first derivative test where our first derivative changes from positive to negative or negative to positive to indicate a maximum or a minimum respectively. Okay, and then we have some concavity. This first shape here is concave upward. If our shape is concave up, then that means our first derivative must be increasing. It has positive slope, which means its derivative, the second derivative, must be positive. If our shape is concave downward, then the first derivative is decreasing. If it's decreasing, has negative slope, its derivative, the second derivative, must be negative. One last thing, and that is, oh, what is that shape right there? That is a possible point of inflection. And possible points of inflection, they're going to happen where your second derivative is equal to 0 or undefined. But there's a little bit more here. You have to change either concavity, you have to, in f of x, your first derivative must be changing from increasing to decreasing or decreasing to increasing, or the second derivative must change signs from positive to negative or from negative to positive. All right, and the rest of this lesson, we're just going to look at a whole bunch of very interesting graphs and use calculus to analyze them and graph them.